Morning, welcome back. I want to remind you of a couple things before we get started. One is we have our next exam a week from today. This exam is going to cover chapter 6. I thought about extending it a little bit more because we're doing chapter 7 already, but we're going to do a review on Tuesday, and then we're not going to get very far in chapter 7. I thought let's just stick it to chapter 6. So it'll be chapter 6 only. We did chapter 5 already. And again, problems similar to the homework. But mostly similar to the practice exam problems. I put some of the more important problems on a practice exam that's now out on D2L, so you can download it. Sort of the previous one didn't get out there. This one's out there on the right web page. So most similar to the practice exam. If you weren't here last time, I think probably all of you were. I said I would give the first exam because you didn't get your practice exam online. It was in the wrong location. I'll make that an optional score. If it improves your score for your grade for the class, then I'll use it. And if it doesn't, then I'll drop it. Plus, you get to drop one more test besides with the syllabus. So I'll grade you on your remaining exams, and if the exam one helps you, then I'll add that in. All right. So look for this. It says practice exam 2.6, I think it is, out there. And you can see the style I usually like to give for exam 2. It'll be on graphs of trig functions, inverse trig functions, and their calculations and graphs. Any questions that you want to bring up based on last time or based on the exam? All right, well, today we'll do, interrupt any time with the questions, take the mute off if you want. Today we're going to continue doing trig identities. This is chapter 7, it's not for this exam, but it will be on the next one. And I mentioned before, this chapter, chapter 7, is probably the hardest of the semester. So its exam you really have to practice a lot for. I think it's just because it's a lot of proofs in there, is what it amounts to. These proofs are actually important because they come up in practice. I gave you an exhaustive list of all the trig identities we've had so far, and the object was then, one, to simplify equations, and we had those rules of thumb. A second application of trig identities is to prove new identities. You can make your own designer identities, I like to say. So another application is proving identities. This is one of the harder parts of the course, but it just takes practice. And when you become good at this, you become even better at simplifying those things. And I think the book problems say establish the identity. They try to avoid the word proof, but it really is proofs. And what we do for these really isn't much different than simplifying. We follow the rules of thumb that we already have. We look for algebraic simplifications, which we listed last time. We look to apply a trig identity to prove a new trig identity. And then if all else fails, we write everything in terms of sine and cosine. All this begins by what we mentioned in the upcoming sections, by making sure every trig function is of the same angle, theta, not some of them of 2 theta and some of them of theta. So you follow the rules of thumb from last time, but when you're trying to establish an equation, you also can work both ends towards the middle, so you can simplify from both sides. Most books seem to say, start with the more complicated side. That's not an absolute rule. If you see a way to go from the other side, great. But that's just again, a rule of thumb. People like to start with the more complicated side and reduce it. But whatever way you see to go, that you prove it works. And you don't have to make the shortest proof, it just has to be right. But also work both ends of the equation to meet in the middle. It's like the two railroads coming from the opposite ends of the country. You have to drive the golden spike in there when you get the proof here. Both work both ends of the equation to a common middle, then you prove the theorem. So there's a whole bunch of things just to practice here, and I just want to show you with a couple of these that really it's just what we already did, simplifying, but working both ends of the equation towards the middle. So here's a nice example, and you've got some in problem 4 on the homework. I want you to work all of them. All the problems in this section. There's only 4 of them, but some of them have parts, so it's more like a dozen by the time you do it all. So here I'll list the homework, 7.1 on the UCO supplement. Problems 1 through 4, that's all of them, right? But they're really good problems. Here's we did simplifying, that's the first 3. Here's some problems out of the 4th one. You can check it as you go along. Suppose I try to prove that cosine x minus cosine squared x equals cosine x times sine squared x. Not an obvious result, right? How could I prove that? Here's the way most mathematicians do it. You write this at left side here, cosine x minus cosine squared x. You keep track of the other side somewhere. I like to write it down at the end, cosine x sine squared x. And you say, how can I make these two ends meet by following our rules of thumb? We said the first step to try on these things typically, and you don't have to do them in this order, it's just what often works. You work through those steps, algebra, trig identity, write in terms of sine and cosine, rotate to the top, algebra, trig identity, write in terms of sine and cosine, and you can kind of rotate those through. Here I notice algebra, I can factor a cosine x out, right? In fact, this is cosine x times, did I write this right? I miswrote this. This is cosine cubed. Sorry. Cosine x times 1 minus cosine squared x. All right, so by factoring, there's step 1, algebra. And now I say, does that look sort of the same? Boy, that looks really close, doesn't it? If only I could make this one and this one match. Here's a thing to know. Whenever you see 1 plus or minus a square of a trig function, think of one of those Pythagorean identities. Well, note over on the side here, we have this trig identity. Sine squared plus cosine squared equals 1. The most fundamental Pythagorean identity of the 3 that we have. One of the more important equations of trigonometry. If I were just to subtract cosine squared from each side, I have sine squared can be replaced with 1 minus cosine squared, right? So keep this in mind whenever you see 1 minus a square of a trig function or 1 plus a square of a trig function, depending on which trig function it is, it reduces. In this case, 1 minus the cosine squared does reduce. 1 plus actually doesn't for cosine, but 1 plus tangent squared does by another trig identity. This can be replaced with sine squared or sine squared with this. And so I might work maybe this end towards the middle and say, wait a minute, I'll replace sine squared with 1 minus cosine squared. Now they match, right? And so this, I could say this is by the Pythagorean identity. And I can say this one is by factoring. So an algebra step here and a trigonometry identity here, I make both ends meet. You don't need to write this twice. We can just put this up here. There it is. And that's a good proof, right? It's only 2 steps. Well, 1 intermediate step, right? Just put this in the middle so I can see that you factored and see that you applied the identity. And it's a pretty easy proof, the first one, right? So that's how a lot of these work. You look for something that looks kind of familiar, and one of these things to get used to is 1 plus or minus the square of a trig function often reduces by one of the Pythagorean identities. And then all those algebra rules apply, right? Let's look at the next one here. I'm going to change this a little bit from the homework problem and do something similar, and then you can try the similar homework problem. Actually, no, I'll do this one also. Actually, let's do sine x plus cosine x squared. Show that this is true, is it actually equal to 1 plus 2 sine x cosine x. I wonder if that's true. How can I prove that? Again, what you do is you write the left side, sine x plus cosine x squared equals, and then you can write the right side down here. I left more space than I needed there, didn't I? Maybe I won't need so much space on this one. But it's better to have too much than too little in practice, so let's leave a fair amount. And they say start with the more complicated side. They're sort of equally complicated, but I just think about it for a second, and what would an algebraist do is the first step, right? Well, when you have a square, you normally multiply it out, right? So let's FOIL here. And again, don't write sine squared plus cosine squared because it's not. You have to FOIL, right? Think of this as sine plus cosine times sine plus cosine because that's what it is, right? That's what this is. You don't have to write this intermediate step. So it's this times this plus this times this plus this times this plus this times this. What you get is this times this is sine squared. This times this is sine cosine. Then this times this is cosine times sine. That's the same thing, right? You can multiply in either order, and it's the same thing. So I got two of those now. And then cosine times cosine is cosine squared. So by FOIL, you can write this out if you want. I'll just say this becomes this. And now I have to convert this into this. How can I do that? Well, a sine squared plus cosine squared, I remember by the Pythagorean identities equal to 1. So this part reduces to 1. Oh, I don't need to put any more steps in at all, actually. I have already got it. All I have to do is say that this is by the Pythagorean identity. Sine squared plus cosine squared is equal to 1. You don't have to draw these arrows either. I just want to be able to see what identity gets me from here to here. Right? So Pythagorean identity. All I had to do was FOIL and apply sine squared plus cosine squared equals 1. So a lot of these, there's an easy way to do them if you, if you think for a second. Even if you don't see this right away, sometimes with a few more steps you can do it. So. These are not too bad in this section primarily because they're going to start with some easy ones, but they will get longer than this as we go, and we'll have more identities to apply. I'll do one last proof here. This is the third one. I'm going to change it around just a little bit. Suppose I gave you this one, and then you can do the homework this is like it. Suppose I said, show that this identity is true. By the way, what is an identity? I should mention it somewhere along the way. It's a theorem? Yeah, sort of. It's a theorem that's true whenever everything's defined. And so this one is actually defined for everything because you can take the sine and cosine of every number. But some of these theorems, maybe one side's defined and one's not, and the identity means it's true whenever everything's defined. If one side's not defined, it doesn't have to hold. So let's say this one. Suppose I ask you to show that the square of the sine minus the square of the cotangent is equal to 2 minus the square of the cosine minus the square of the cosecant. All right. Suppose I ask you to prove that one. Remember our rules, when you see 1 plus or minus a square, sometimes that comes out to be something simpler. All right, so we'll think Pythagorean identity. I see some squares of trig functions. These come up a lot in practice, squares of trig functions. And I'll put the left side here, and I'll put the right side here, and I'll try and work both sides towards the middle. And this is where a little bit of intuition helps. there's a 2 here, not a 1, but if I put this instead as 1 minus cosine squared plus 1 minus cosecant squared, then I'd have 1 minus the square of a trig function, 1 minus the square of a trig function. Maybe that will reduce by a Pythagorean identity. So I'll start right here, not by doing something that simplifies it, but by something that actually makes it longer in order to be able to apply a trig identity. So these are by hook or by crook. Sometimes a clever step is to not just simplify, but to see a way to apply a trig identity. So this is just by algebra here, right? I just wrote 1 plus 1 is 2. And then put the parentheses in a little different order. All right. And now I say, well, wait a minute. What's the trig identity that we have? We have sine squared plus cosine squared equals 1. And maybe it's hard to remember the trig identity with cosecant squared. And that's the hardest one to remember. But remember, you can figure these out if you equals 1. If you divide this through by sine squared, then sine squared over sine squared is 1. Cosine squared over sine squared, you can kind of visualize this as cotangent squared. And 1 over sine squared is cosecant squared. So I can figure this one out from this one if I forget it. Well, let's see. Now, if I subtract cosecant squared over here, I have 1 minus cosecant squared plus cotangent squared, 0. And then I could subtract cotangent squared over there and rewrite it as 1 minus cosecant squared equals minus cotangent squared. 1 minus the square of this trig function that I have, it can be replaced by minus cotangent squared. That will simplify it. So now I'm simplifying. Let's see, I'm working both ends towards the middle. In this case, I'm working backwards towards this one. Right? And so 1 minus cosine squared from this one, right? If you subtract cosine squared from both sides, you observe that sine squared 1 minus cosine squared. So I'll replace 1 minus cosine squared with sine squared. And I'll replace, let's see, there it is, 1 minus cosecant squared with minus cotangent squared. So I'm applying the Pythagorean identities to them. Sometimes I can't write and talk at the same time. So this is minus cotangent squared by 2 trig identities, Pythagorean identities. Oh, there it is. Right. So done a clever way, you can do this in a couple steps. It's just not long at all. And it looks real easy in here, but it's like watching a professional ice skater. They make it look so easy, but boy, those are not easy moves, and these aren't either. Sometimes getting this intuition is important. That's why I said in this section, this chapter, more than others, you want to practice. That's what gives you the intuition to rewrite this as 1 minus the square and 1 minus the square. Those kinds of intuitive things are real helpful. If you didn't get this way, if you didn't have that cleverness to write 2 minus this is 1 minus and 1 minus, there are other ways to go about this. A good idea, remember, when you have more than 2 trig functions in the expression, or if you just are stuck, is to rewrite everything in terms of sine and cosine. Another good way to prove this would have said, well, we could write sine squared minus cotangent squared. If I just don't know what to do and I don't have that clever manipulation there, is sine squared minus, rewrite cotangent squared as cosine squared over sine squared, right? Cotangent is cosine over sine. Square of cotangent is square of cosine over square of sine. So I could rewrite it like that. And then the other side, get rid of this. So again, I'm trying to do the same proof, working both ends towards the middle, but this time I'm going to do it differently. So I'm trying to get down to 2 minus cosine squared minus cosecant squared. So I'll apply the rule 3 that says rewrite everything in terms of sine and cosine here, and I'll do the same on the other end. I'll say that this one, if I write cosecant squared, this would be 2 minus cosine squared minus 1 over sine squared. Right? And so now I start to see, can I make this work out? Well, it looks hard, but you know, if I put everything over a common denominator in algebra, that sometimes makes things look equal. And so I could instead, so this is an alternative proof, I should write. It's much longer to do it this way. That's why practice brings cleverness and makes these proofs short. All right, so I work this into here and I work this into here. I'm trying to make them the same. What you can do when you see the same denominator, all I have to do maybe is put them over a common denominator. So let's see if I can do this. Let's see if I can sign. I want to make sure I didn't make a mistake here. Yeah, let's I mean, there's a lot of ways to proceed from here, actually. One thing might be to say, well, I have 1 over sine squared here, and I've got cosine squared over sine squared here. Maybe what I should do is apply the Pythagorean identity and write cosine squared as 1 minus sine squared. There's a good thing to try. So it makes it longer for the moment, but now I have 1 over sine squared like I did here, and I'm trying to make the two ends match. So see, I should have left more room in the middle this time. Do it this way. All right, now, let's see. 1 over sine squared minus 1 over sine squared matches this one, so I'm going to pull that out. I'll write this as sine squared minus 1 over sine squared. This over this. Minus a minus becomes plus sine squared over sine squared. And so I just take this quotient, right, as 1 over sine squared minus sine squared over sine squared, right? From algebra. So that's an algebra step. Go from here to here. Algebra. This one was writing sine and cosine only. Which is a trig identity, but I like to point out what we're doing. And then here, again, I try and get sine and cosine. But the idea is if you're really stuck, you try and write both ends as sine and cosine only. And then you try and make them meet by kind of like algebra. And they say, well, wait a minute, sine squared over sine squared is 1. So this is sine squared minus 1 over sine squared plus 1. Right? And these already match. Oops. These already match. Minus 1 over sine squared minus 1 over sine squared. Well, I've got 2 minus cosine squared. Is that equal to sine squared plus 1? Sure it is. I can rewrite, when I see a sine squared here, I can rewrite it as 1 minus cosine squared. So I can rewrite this as 1 minus cosine squared instead of sine squared. Now I've got the cosine squared that I want there. And then minus 1 over sine squared plus 1. And now I've got it, look. Minus cosine squared, just like here. Minus 1 over sine squared, and 1 plus 1 is 2. So I can, here by addition, I get to the next step. So there with a lot more work, I can fumble around and make the ends meet just thinking kind of algebraically. I replace everything with sines and cosines. I'm sorry, I didn't leave more room in the middle now, but this is what happens when you don't leave enough room. I'm showing you what you should not do. It's the Berenstain-Bears lesson, right? Leave enough room in the middle, right? Plan ahead. And you can, by writing in terms of sine and cosine, trying to match up the term by term, and here we get minus 1 over sine squared both, and we try and get the other terms. We can make this meet the long way, and I'll give you 100% on this one too. That was just an illustration of what happens in a lot of things. Any questions on all that? The easy way or the hard way? I guess the easy way is sort of erased. All right, so we're going to push it to the next level. The rest of this chapter is mostly, and there is some other stuff, and you'll see it pretty quickly. It's mostly about adding some new identities that are also very important, and just doing this again. So you get a few more identities, and with those you now simplify and derive new trig equations. And you get some more identities, simplify and derive new trig equations. And there's a few additional results along the way. For instance, we'll get some new angles that we can find exact values for the trig functions of those angles. It's going to turn out that every multiple of 15 degrees is now going to be easy to find the exact value for all the trig expressions using something called half-angle identities. All right, so here's the next topic is going to be the sum and difference identities. This has a wonderful proof, but it's too long to be useful. I try and do the ones that are short and insightful. This one isn't insightful at all, and it's long, so we won't do it. But you can look in your book and see it. It's kind of a neat geometry proof. But you just memorize these. Here's the theorem, the identity. When everything's defined. Actually, we don't even need that statement on this one. Theorem, sine of x plus y is sine x cosine y plus cosine x sine y. That's called a sum identity. So let's put this in here. Sum and difference identities is what we're going to write now. These are defined for all x and y, so I'll just say theorem here. There's the sum identity. Now, one nice thing about these, even though there's 4 of them, 2 of them can be derived from the other ones. Well, let me put this one down. Cosine of x plus y turns out to be cosine minus sine. That's how we usually say it. It's easier to remember rather than saying sine of x plus y, sine x cosine y plus cosine x sine y. That's hard to memorize. What you do is you say sine of the sum is sine cosine plus cosine sine. That's the sum identity. Sine of the sum is sine cosine plus cosine sine. Cosine of the sum is cosine cosine minus sine sine. And so it's easier to remember with that kind of rhyming almost. Now, those are the sum identities. All right? We also need difference identities. And I just want to make a note, if you forget these, you can figure them out. If you were to put minus y instead of y in this one, so I'll do a derivation. Then you would have sine of x plus minus y is sine of x minus y on the left, right? Just using this theorem that we already have. You can prove this on the unit circle, it turns out. And so then it is equal to sine x, and we replace y with minus y, so it's cosine minus y, plus cosine x, sine of minus y. So just replace, this works for all angles x and y. So if it works for y, it also works for minus y, whatever angle y is. And we can say by this first identity that we prove on the unit circle, we can then prove this one. I mean, we just replace y with minus y. This must hold. So this is a proof here. This is actually proving the next identity. This is kind of what you want to do in the homework, right? But now cosine of minus y, cosine is an even function, so the minus goes away. It's sine x cosine y. On the other hand, sine is an odd function, the minus comes out. And you get cosine x, sine of y. And by the way, so the minus came out and went there. Often I will drop these parentheses. These are functions, so it's like f of x. In practice, you really want to put the parentheses on. But you'll see everybody, including books, when it's sine of x, we get tired of writing those parentheses. Everybody knows if you write that, it means sine function of x. So often I'll write this without the parentheses. And it means the same thing. Right? So that saves a little writing if we can do it that way, not put all the parentheses on. I think I'll put it in the first step and then not in the next one. There's a new identity. All you have to do is replace y with minus y in this one to get the sign of the difference formula. Sine of x minus y is sine cosine minus cosine sine. So here's the next one. That's the proof. maybe I should say to prove, that the sine of x minus y is sine cosine minus cosine sine. There it is. So even though these are going to be 4 identities, in some sense, if you can memorize 2, you can immediately get the others just because it's an obvious immediate application of the even odd identities. And similarly from this one, we can prove the difference identity for cosine. You accept this one, which actually can be proved from this one, the cofunction identities. Suppose in this one, we try and prove a difference identity for cosine. If we just put, this is a short insightful proof, that's why I'm doing it, put minus y in here, in this equation, to prove, similarly, on the left, cosine of x plus minus y is just cosine of x minus y. And on the right, then we get cosine x, cosine minus y. Oops, wrote this wrong. Yeah, no, that's right. Yeah, cosine x, cosine minus y, minus sine x, sine minus y. So put minus y for y in this one. It holds for all y. In particular, if it holds for any plus y, it also holds for minus y. And you get this. But now the even odd identities, again, cosine of minus y is cosine y, so I just replace it with such. And then sine of minus y, the minus comes out and cancels this minus, and I get plus sine x, sine of positive y. There's the identity for differences. All right? Cosine of x minus y is cosine, cosine plus sine, sine. That's all there is. So you have 4 new identities memorized, but really, it's tantamount to memorizing 2, because you can figure out the other 2 immediately by the even odd properties of sine and cosine. Sort of a one step in the middle proof, like the other easy one we did. But you have to know all these. What we're doing now is we're going to add these to our list of familiar identities that we wrote last time. And when we see something in an equation that needs to be simplified, we can apply these. If we need something to prove an identity, we can apply these now. So it's just 4 more formulas added to what we already have. And we'll see if we can do the same things with those. Can we simplify expressions? Can we prove identities? And then there's going to be some more applications too of these shortly, besides this, what we did. Here's an interesting result here. Simplify, right? We did simplifying expressions last time. Suppose somebody gave you this expression, sine 2x cosine 5x minus sine 5x. Next I'm going to write it a little simpler. Yeah, all right, minus sine 5x cosine 2x. And I'm asked to simplify that. Can I make that simpler? Here's what I call the duck rule. If something waddles like a duck, right, and it quacks like a duck, and it swims like a duck, it's probably a duck, right? So what does this look like? What does that look like? If I think back to this thing here, and I think of this as some other angle alpha, and this is some other angle beta. This looks a lot like sine, cosine, plus sine, cosine, minus sine, cosine. If I reverse the order of these, I wrote it as sine alpha, cosine beta, minus cosine sine. It sounds like the rhyme, right? Sine, cosine, minus cosine sine. And sure enough, in fact, let's circle these here. thinking of the identity over here, this is the difference identity, right? Sine, cosine minus cosine sine of any two angles is sine of the difference of the angle. So if I think of this as an angle alpha, and this is an angle beta, alpha and beta, sine, cosine minus cosine sine of alpha and beta is sine of the difference, alpha minus beta. Right? Sine alpha cosine beta minus cosine alpha sine beta is sine of alpha minus beta by the second one of those, the difference identity for sine. But I just had to rearrange it, put this multiplication in the opposite order, which you can always do, right? You can multiply numbers in any order to see it. But use that duck roll. Boy, that quacks like a duck. And put it in the right order. And now, what's alpha? Alpha was 2x, and beta was 5x. And so this is actually sine of 2x minus 5x, which just by arithmetic or by algebra, I guess you'd say, reduces the sine of minus 3x. And now what we usually do in these, when there's a minus in here, we apply the even or odd identity to simplify it, pull it out. So we'll say this is minus the sine of 3x is the usual way of writing that. Look how nicely that simplifies. We know exactly how to graph this, right? It's just got period 2 pi over 3, and it's flipped upside down. And I can sketch it immediately, where this was not so obvious. What kind of wave is that? But the identity proves it's just a simple sine wave. You take the basic sine function, reduce the period to 2 pi over 3 and turn it upside down, and you can sketch this one. You know exactly what it looks like. Any questions on that one? Not getting a lot of input today. I want to make sure I'm not missing an important point here. All right, I'm going to do another one. I want to leave these identities up here. This is actually an extremely important one here. This is the next section coming up, actually. Suppose I want to prove this identity. All right, so I did a simplification there. That's one thing we did before. And now we just got some more identities to apply. Suppose we want to do this simplification. Show that, or establish that, cosine of twice x is the cosine squared of x minus the sine squared of x. Boy, if it was just cosine squared plus sine squared, it'd be 1. But now what's cosine squared minus sine squared? Turns out it's actually equal to cosine 2x. So the difference of the squares actually simplifies too, as well as the sum of squares. Not as nicely, but it does simplify, right? So cosine squared plus sine squared is just 1. Cosine squared minus sine squared is cosine of 2x. How can we show that, right? Again, you go back and you just do the same rules of thumb. Where both ends toward the middle. It's just I have some new identities I can apply. So here's the two ends, cosine 2x, and this time I'll leave a little more room. I don't need much for this one, it turns out, but if I didn't know that, I should leave lots of room. How do I show that? Well, it's the rule 0 that we haven't had to apply because I said it didn't apply last section. It doesn't apply to this section. Whenever you have an identity that has more than one angle, here we have x on this one and we have 2x on this one, we got to get rid of that double angle. So what can we do by following our rules of thumb? The first thing to do is rewrite this as cosine of x plus x, and then say, there it is, cosine of a sum is cosine cosine minus sine sine. So this is going to be cosine cosine minus sine sine. Only difference is instead of x plus y, we have x plus x. So in there we put x for both angles. Cosine x minus sine x. There it is in the next step, right? Cosine times cosine is just cosine squared, right? This notation means this. And sine times sine is sine squared, I should have put. Sorry about that. Right? That's what this notation means. And so there it is. It's just a one step in the middle proof. From the sum angle for cosine, we get immediately that cosine 2x is cosine squared minus sine squared. How about that? That's an important identity to memorize. We'll call that a double angle identity. Here's another one. Show that the following holds. Sine 2x. Here's a double angle identity for sine. This is actually equal to 2 sine x times cosine x. How can we prove that one? Once again, with these sum and difference formulas. We start from the left side, sine 2x. We want to finish with the right side, 2 sine x cosine x. All right. How can we do that? Rule 0, right? We've got two different angles, 2x and x. So I'll rewrite this as sine of x plus x. And this time apply the sum identity for sine, right? Sine of the sum of two angles is sine cosine plus cosine sine. That's why you have to memorize these little rhymes. Sine cosine plus cosine sine. It's just now the two angles are the same. Instead of x and y, we just got x and x. All right. Now you can multiply in either order, so you can write cosine times sine as sine times cosine. And lo and behold, two of these. There it is. So there's the steps. I left just enough room on this one. There's the proof that actually this is true. Moreover, this is a really useful thing in practice. It comes up a lot in science and engineering and other places. This is called a double angle identity. We want to memorize that. We've got our new own designer identity here. Somebody else has thought of it first. All right. But you can see that using the identities you have, you can prove a lot of new, very useful identities. And these come up a lot in practice, the double angle identities. All right, so I'll say memorize those and then memorize these. Look at that, 6 new identities to memorize today. However, if you can memorize these two, you can figure out these two from the even odd properties if you ever forget them, right? And it's sort of two. I want to make a point here. If you don't like memorizing 4 of these, here's an easier way to memorize these. Now, I'll try to make this a little easier as we go. Here's how you can memorize it sort of as two. In addition to saying it's the even odd property, say sine of x plus or minus y is sine cosine plus or minus cosine sine. So I like to write it this way sometimes. Right, and the plus goes with the plus and the minus with the minus, right? And then you got both identities in one. Similarly, cosine of x plus y here and here, these two can be written as cosine cosine minus or plus sine sine. So if you don't like memorizing 4, you memorize these two just with plus or minus on both of these and plus or minus here and minus or plus here. And this gets both of these identities. So these are actually easier to memorize if you like. You can do it either way. Now it's only 4 identities, right? These two and these two. The sum and difference identities and these double angle identities. All right, so now I can erase this part since I've got it in brevity down below. And we can do the same things. We can simplify trig expressions, but new ones now because we have new identities. And we can prove new identities like these double angle identities that are so important. But there's an additional application. We can also now evaluate trig functions exactly at some new angles. In fact, any angle that's a multiple of 15 degrees. Well, I won't call those special angles, but they are special, right? And how do you do it? Using the sum and difference formula. And then 15 degrees in radians is pi over 12. Before you wanted a multiple of pi over 6 or pi over 4. Now just any multiple of pi over 12, and then encompasses both cases. And before it was any multiple of 30 or 45 degrees. Now it's just any multiple of 15 degrees, which encompasses both those cases. So we've got a new bunch of angles we can evaluate things at, and really, rather than writing out the formal rules, I think you just see an example and say, oh yeah. The idea is just any angle that's a multiple of 15 can be written as a difference of two special angles. Maybe I should write that out at least, because such angles are a sum or difference of special angles, the ones we've already done, multiples of 30 and 45 degrees. And so we just have to write them that way and apply these sum and difference formulas. This star here, maybe I should call this equation 1 or something. Here's an example. Suppose I wanted to calculate exactly the sine of 15 degrees. I could not do that before. Right? Like some of these calculators will tell you what it is exactly. A lot of them will, because they have these abilities to use these identities. How can I find the sine of 15 degrees exactly? What you do is you write it as a sum or difference of special angles. I know that 15 degrees, for instance, is 45 degrees less 30 degrees, right? Now, if I think of this as x, what? This is y in the formula. My difference formula, sine of x minus y is sine, cosine minus cosine sine, with x 45 and y 30. I come up with this, sine, cosine, minus cosine, sine. And let's see what it is. 45, 30, 45, 30, replace x and y. And these are, since these are special angles, I can evaluate these on the unit circle. That's how it works. You write any multiple of 15 degrees as an angle that's a sum or difference of special angles. Apply the sum or difference identities, and now you can evaluate the resulting angles on the unit circle. In fact, if these turn out to be acute angles, you don't even need the unit circle. You can do this with special triangles. I'm going to go ahead and erase this just to have these memorized pretty well. So now I'll say here's a 45 degree, 90 degree triangle. I remember the three sides on this, square root 2 over 2, square root 2 over 2, 1. And so I know the sine is opposite over hypotenuse is square root 2 over 2. I should have written this over a little further, but put it over here. And then the other triangle I have can take care of the 30 degree angle. If I put the 30 degree angle up here, let's say, I know that the short side goes opposite that, the square root of 3 over 2 goes opposite the larger angle, 60 degrees, and this side is 1. And there's the 30, 60, 90 triangle. I look at these, say sine of 45 degrees is this over this, is square root 2 over 2. Cosine of 30 degrees, here's this angle adjacent over hypotenuse is square root 3 over 2. Cosine 45 degrees is adjacent over hypotenuse is square root 2 over 2. And sine 30 degrees here is opposite over hypotenuse is 1/2. Now I notice that this one is square root 2 times square root 3. That comes out to be square root 6. Actually, maybe we should, let's see. No, that's good. Square root 6 over 4. And this one comes out to be square root 2 over 4. I notice there's a common denominator, so I like to combine those, and we'll say this comes out exactly square root 6 minus square root 2 over 4. There it is, the sine of 15 degrees exactly in terms of roots. Let's try a little harder one. That's the easy one. instead, I wanted to calculate maybe cosine of 195 degrees. I wonder what the cosine of 195 degrees is. Well, if you think about it, it's a multiple of 15. And here's a little intuition that goes into this. How do I know it's a multiple of 15 just by looking at it? I think it's not real obvious to me. If you notice that 195 degrees is 180 plus 15, that's pretty obvious, right? All previous special angles, including quadrantal angles like 180 degrees, are multiples of both 35. All the quadrantal angles are multiples of both 30 and 45 degrees. So if you can add any 15-degree angle to a quadrantal angle to get this, then this will be a multiple of 15 degrees also. So, right, 180 is a multiple of 15, 90 is a multiple of 15, 270, 360, all those quadrantal angles are multiple of 15, as are the special angles. And so any special angle, including quadrantal angles, plus a multiple of 15 is again a multiple of 15. So I know this one is going to be a multiple of 15, or you can divide it in and see, right? So because it's a special angle plus 15 degrees, it will be a multiple of 15 degrees. That's how I figured it out. Now you can take a big angle, right? Like 735 degrees. I know that's a special angle because that's a multiple of 15 degrees because 720 is a multiple of 15 degrees. Add 15 degrees and I get 735. Right? So those kind of things. Now that means that I know I can write this as a sum or difference of special angles, right? How can I do this one? There's actually lots of ways to do this. The trick is to find one that's not too hard, right? One way I could do it is say, well, it's 135 degrees plus 60 degrees. There's nothing special about this choice particularly. You just don't want to choose 1,000 degrees and 900 degrees or something like that. One of these big numbers, you don't have to. But that's about probably as easy as I can write it. And these two add up to 195. And I remember that 135 is a special angle. It's a multiple of 45. And 60 degrees being a multiple of 30 is a special angle also. So now I apply the sum of angles identity for cosine. So this time it'll be a sum formula for cosine. So if I think of this as x and this is y, remember cosine of x plus y is cosine minus sine. For the cosine identity, plus goes with minus. For the sine ones, the plus goes with plus and minus with minus, but for the cosine, plus with minus and minus with plus. You remember the identity. All right, so this is cosine of 135, cosine of 60, minus sine of 135, sine of 60. And these identities put the sine angles in the same order. X, Y, right? Now what are these? Since they're special angles, I can get them exactly on the unit circle. And I do that. Cosine 60 degrees, once again, since that's an acute angle, I can just use the special triangle. There's the 60 degrees. Here's 1/2, square root of 3 over 2, and 1. And I observe that cosine 60 degrees is adjacent over hypotenuse is 1/2. And then sine 60 degrees is opposite over hypotenuse is square root of 3 over 2. So I've got two of the numbers from that triangle, right? I use the 60-degree 30, 60, 90 triangle for both those. Now I need the 135. Since that's not an acute angle, I'm going to have to appeal to the unit circle here. On the unit circle, I sketched in standard position the angle 135 degrees, which I remember is 90 plus 45. That leaves this one as a 45-degree angle, right? 135 and 45 add up to 180. Or this is 45, so this is 45, adds up to 90, either way. Drop the perpendicular. Since I have 45, 45, 90 triangle, I know this is square root 2 over 2, this is square root 2 over 2, and this is 1. That's the one that fits in the unit circle. Now I observe the cosine is the x-coordinate and the sine is the y-coordinate. You have to go by the coordinates, not the lengths, right? So the x-coordinate is minus square root 2 over 2, but the y-coordinate going up is plus square root 2 over 2. That means the cosine is minus and sine is plus. Cosine of 135 degrees is minus square root 2 over 2. Sine of 135 degrees is plus square root 2 over 2. There it is. The unit circle gets the obtuse angles, and the simple triangle gets the acute angles, and you can get these expressions exactly. Now I have the cosine of 195 degrees exactly. Here it is. But once again, what happens in practice is that you can put these over a common denominator to simplify them. So this one, again, with quotients, top times top over bottom times bottom makes this minus square root 2 over 4. And this one, top times top over bottom times bottom, multiplying the square roots. Remember this property, I said it before, but square root of a times square root of b for any non-negative numbers, ab is square root of ab. You can combine these. So this is square root 6 on top here, and 4 on the bottom. And this one, I get minus, if I simplify it, square root 6 plus square root 2 all over 4 by combining these. So a little different, but also happens to have square root 6 and square root 2 in there. There is exactly, in terms of square roots, the cosine of 195 degrees. How about that? And you start to observe, yeah, sure, I could get, now doing the same thing, the exact value of sine or cosine for any multiple of 15 degrees. And we can do it in radians too, making these progressively a little harder. Suppose I wanted to find the secant of minus pi over 12. Can I do that exactly? Sure I can. Remember, pi over 12 is 15 degrees, so this is certainly multiple of 15 degrees. It's minus 1 times 15 degrees. So how do I do this one? Here's a hint. You can save yourself a little trouble on these by applying the identities along the way sometimes. Secant is an even function, so I can say secant of minus pi over 12 is the same as secant of plus pi over 12. Why deal with that stupid negative the whole way through when I don't need to, right? So let's get rid of it right off by the even identity. I'm always dropping a minus sign here somewhere, there, another place, maybe save me an error later. Now I don't have a sum or difference formula for secant. Why not? There is one, actually. You can derive it from the cosine difference, but nobody memorizes it because you can always figure this out by writing it as 1 over the cosine of the same, right? 1 over cosine of pi over 12, and use the cosine identity. So this is your reciprocal identity. See how useful these identities are, but you just have to practice at them, right? And then now I can use the sum or difference identity for cosine. And I don't need to memorize that big klutzy thing for secant. People hardly ever use that. There is one, but I mean, you just write 1 over cosine is easier, right? All right, so 1 over cosine pi over 12, all right. So remember how to do a cosine of an angle that's a multiple of 15 degrees, which is pi over 12? You write it as a sum or difference of special angles, right? So I'll write, instead of cosine pi over 12, I'll write it as cosine of pi over 4 minus pi over 6. How did I know to do that? Sort of practice again. I told you practice is important. But basically it's fractions. You say pi over 12, just think of 1/12. How I can write a 12th instead of in terms of fourths and sixths, 30 degrees and 60 degrees. I can write, let's do this, 1/12 is what? It turns out it's 1/4 minus 1/6. You can write 1/12 as 3/12 yeah, all right. minus 2/12. All right, so 1/12 is 3/12 minus 2/12 is the same as 1/4 minus 1/6. For this class, it might behoove you to memorize that, right? But if not, then you can figure out 1/12 is 3/12 minus 2/12, right? 3 minus 2 over 12 is 1/12. And then you can write this one as 1/4 and this one as 1/6. And now, if you have pi over 12, you just think, oh, pi over 12 is 3 pi over 12 minus 2 pi over 12 is pi over 4 minus pi over 6. There it is. So that's how you can figure that out. You can write it in terms of angles that are multiples of pi over 4 and pi over 6 in radians. You can see it's a little harder in degrees. You have to practice this. But you know, it's just fractions, right? And then put a pi on it. Now, cosine of the difference. Cosine x minus y. Remember, with cosine, minus goes with plus and plus with minus. So cosine of the difference is cosine, cosine plus sine, sine. So I'll put cosine x, cosine y, plus sine x, sine y. Cosine, cosine plus sine, sine is the difference formula. Starred, equation's 1. I should put that in y1. And now these are all special angles. I can do them exactly. Moreover, they're acute, so I can do them just with the triangle. So here's pi over 4. I memorized this one. See why you need to memorize these? They come up all the time in this section. And here's the other special triangle, the 30, 60, 90. And this time I'll call this pi over 3 and pi over 6 for radians instead of 60 degrees and 30 degrees. And over here, instead of 45 degrees, I'll put pi over 4. And now let's see, the cosine is adjacent over hypotenuse, is square root 2 over 2. Cosine of pi over 6, this angle is adjacent over hypotenuse, is square root 3 over 2. Sine of pi over 4 is opposite over hypotenuse, is square root 2 over 2. And sine pi over 6, this angle is opposite over hypotenuse, is a half. There it is exactly, the secant of minus pi over 12. Well, no questions, this stuff must be easy, huh? That's pretty hard, huh? Now, I can't accept an answer like that without taking something off. This is not simplified, right? So what do we do? And now it's just, sometimes the algebra on these honestly gets harder than the trigonometry. It's just the way it is. Use the trigonometry to get here, and then sometimes simplifying this is actually even harder. But let's do this. Once again, we'll write this as a single quotient, square root 6 over 4. And we'll write this one as a single quotient, square root 2 over 4. Now, what can we do with that? Oh, yeah, we can combine common denominators. See how algebra plays in here? Right, this is 1 over square root 6 plus square root 2 over 4. And how do I simplify that, right? Remember, 1 over a quotient is the quotient upside down, right? So you just rewrite this by algebra again. It's 4 over square root 6 plus square root 2. But your algebra troubles have only just begun. How do I simplify this? We haven't talked about it this semester. We're going to hone your algebra skills and make you experts in this course. This actually needs to simplify still. It's still a point or two off for not simplifying if you leave it like that. Here's the rule. When you see an expression an expression like this, let's say with 2 square roots, you can multiply the top and bottom by what we call the conjugate of this. So this is 4 over square root 6 plus square root 2. I can multiply the top by square root 6 minus square root 2, and the bottom also by square root 6 minus square root 2. Now watch what happens, right? The A plus B times A minus B formula from algebra, right? Becomes this times this is 6, right? Square root of 6, square root of 6. This times this is minus square root of 6, square root of 2, which you can write as square root of 12 if you like. I'll just write this for clarity. And then this one is plus square root of 6, square root of 2. And this times this is minus 2. And what always happens if you have square root plus square root and square root minus square root is these middle terms cancel and you get rid of the square root. They fall out in the denominator. We say rationalize the denominator, right? If you get rid of these radical signs, the root signs in the denominator, rationalize the denominator. We say 6 minus 2 is easy. That's 4, right? So this is 4 times square root 6 minus square root 2 all over 4. And now look at that. The 4's cancel. And this whole answer is just square root 6 minus square root 2. No wonder I'm going to take a few points off if you leave it here, right? This is just square root 6 minus square root 2. So a lot of these, what happens is you have to use your algebra skills and reduce them substantially. And look, the algebra did take longer than trigonometry there. A little bit, I think. But that's what happens in practice a lot when you do these angles of that are multiples of 15 degrees, but not special. All right, now we've done all the works there. Except one thing. One more hitch in our get along here, they say. We haven't considered all the functions. We've done sine and cosine, and we've seen we can do secant, cosecant by just taking 1 over sine and cosine. What do we do with tangent and cotangent? We haven't done those. All right, well, let's see. Finally, we can do sum and difference formulas for tangent. Here they are, tangent. Let's put them 2 and 1 again so we don't have to do extra memorization. Tangent of x plus y is tangent plus or minus tangent over 1 minus or plus tangent times tangent. There are the two tangent identities, one for sum, and again, the top goes with the top, so it's tangent of x plus y is tangent plus tangent over 1 minus tangent tangent. That's the way I remember it. And if it's minus, I'm sorry, I should put minus here. The bottom goes with the bottom. Tangent of x minus y is tangent minus tangent over 1 plus tangent tangent. The way to remember it is it matches the sign on top, plus with plus or minus with minus, and then the bottom one's the opposite. So this one is hard to memorize. When I was a trig student, I couldn't remember this one. Maybe it would help you to see the proof. You can prove it with the sine and cosine identities. Rather than do that right now, I think I'll do an example of this and make sure we can do the homework. Again, the homework isn't due on this immediately. This will not be on this exam. All these sum and difference formulas that we did today are not for this exam. They're chapter 7. This exam will be chapter 6 on graphs of trig functions and inverse trig functions. But this will be the next stuff we'll do as soon as we come back after next week. On Tuesday, I think we'll just do review for the exam. I want to make sure we really sink that material in. It's all very important. And then the next week we'll come back and try and recover this. But do keep up on the homework on this and be ready when we come back after the exam. Right? This is hard material, hardest of the course, I think, as you can see. Now suppose we want to do this one. Suppose we want to similarly find the tangent of 75 degrees. What is the tangent of 75 degrees? And by the way, we don't need a sum and difference formula for cotangent. Why not? But you can guess. If it's cotangent of a multiple 15 degrees, just write it as 1 over the tangent. So now we've got everything with this one. If we see one of these cofunctions, we'll just, either the cotangent or the secant or the cosecant, we'll just use a 1 over the identities we memorized, right? So here's the tangent 75 degrees. How can I write 75 degrees as the sum of special angles? Easy, right? It's just 45 plus 30. So try and do the easiest one you can. I can also do 135 minus 60, but then I've got bigger angles. I've got to go to the unit circle instead of the triangles. do something easy. 45 plus 30 is easier, right? Less likely to make a mistake. If I write in the sum of special angles, I can do it exactly using the sum of difference formulas. Treating this is x and this is y, we can call this formula 2 or something, and then say by equation 2 with the plus, the top one, sine of x plus y is tangent plus tangent over 1 minus tangent tangent. So this is tangent plus tangent, tangent of x plus tangent y, over 1 minus tangent x tangent y. There it is. And I know I can take the tangent of all those angles because they're special, right? I feel like Barney saying special all the time, but that's what all the books use anyway. So it's equal to that, and now I just have to be able to evaluate these things. So I'll run again to the triangles, or you can use the unit circle if you prefer. There's a 45, 45, 90. Should have just left it once, shouldn't I? That's your other Berenstain thing today. Is, prepare ahead of time. Just put these up once and leave them up there. All right, so there's the other special triangle. And I'll say this now is equal to, what's the tangent of 45 degrees? It's this one. It's opposite over adjacent, right? Tangent opposite over. But that's square root 2 over 2 over square root 2 over 2. They cancel each other. That's just 1. Maybe you memorize that anyway. Tangent of 45 degrees is 1. What's tangent of 30 degrees? Here's the 30 degree angle up here. Opposite over adjacent. It's write this one out. This is harder. Tangent of 30 degrees is opposite square root 3 over 2 over, 1/2. Maybe I should write it out. Huh? 1/2 over square root 3 over 2. Opposite over adjacent. And now these 2's, both being denominators, cancel, and I just get 1 over square root 3. And then similar, let's write this one out. Tangent of 45 degrees is opposite over adjacent. It's square root 2 over 2 over square root 2 over 2 is 1 since everything cancels. And so I put in 1 for this one and 1 over square root 3 for this one. Or if you like, you can write this as square root 3 over 3 and rationalize it. I'm not going to do that because I'm going to have to rationalize later anyway. But you can certainly do that if you want. 1 minus 1 times 1 over square root 3. There it is. Our answer is 1 plus 1 over square root 3 over 1 minus 1 over square root 3. And now, if that's not bad enough, the algebra is always worse. Right? Let's see how much time I have. Boy, really short on time. But when you see denominators or quotients in here, you always get rid of compound quotients, right? How do I get rid of these compound quotients, right? Quotients of quotients. I multiply top and bottom by the least common multiples of the denominator. There's only one denominator, square root 3. So I just need to multiply top and bottom both by square root 3 to get rid of those. All right? Now the top is square root 3 plus 1, and the bottom is square root 3 minus 1. There it is. And actually, this is still not as simplified as I'd like. How do I make that simpler? Conjugates, of course, right? Whenever I have a root in the bottom and a sum or difference, I multiply top and bottom by the conjugate. If this is minus, I multiply by plus. If it's plus, I multiply by minus. So I'll write this as square root 3 plus 1 on the top, and square root 3 minus 1 on the bottom. And I multiply top and bottom by square root 3 minus 1. Must be getting near the end. My pen is wearing out. All right. Oops. I'm sorry. Plus 1. So it's the conjugate of the denominator. If it's minus in the denominator, you multiply top and bottom by plus. All right. Now on the bottom, I'll get the same thing. The roots will cancel out. This time this is 3. This time this is plus square root 3. This time this is minus square root 3, and they cancel. And then I get minus 1 times 1 is minus 1. So ignoring the canceling terms, I just get 3 minus 1. On the top, not so. It doesn't cancel. They're not conjugates. Square root 3 times square root 3 is 3. Square root 3 times 1 is square root 3, and square root 3 times 1 again is 2 square root 3. I'll do this fast because I'm about out of time. So FOIL, this times this times this, and this times this combined to 2 square root 3s, and this times this is 1. Evidently, I have 4 plus 2 square root 3 on top, and 3 minus 1 is 2 on the bottom. And I'm almost done. Now I have to notice that there's a common factor. I can write the top as twice, 2 plus square root 3. And then once 2 multiplies the whole top, then these cancel. Don't cancel this 2 with this 2. They don't, right? 2 has to multiply the whole numerator and the whole denominator to cancel. You can think of this as 2 times 1, right? They cancel, and the answer here is then 2 plus square root 3. I want you to get it all the way to there as simple as possible. There's the exact tangent of 75 degrees. All right, time to go. You can, boy. Let's just say, look at 7.2, number 1, when you have time, but this is not for this test. Thank you very much for coming in this morning. Any last second question? All right, bring me questions next time. I think if you bring those at the beginning, there's a lot more to be learned. So thank you for your time, and we'll review next time.